recording is on. Yeah. Cool. Pleased to have Adithya giving a talk today. Adithya is a PhD student at CMU LTI with Teruko Mitamura. We had a good chat. Works on interesting problems in long context language models related, especially focusing on like multi-doc summarization as an interesting, compelling task to study language models. Adithya's work has won multiple paper awards at top NLP conferences. Yeah, excited to hear your talk. So go ahead and take it away. And maybe before you start, just like give like a heads up to people if you prefer questions at the end, throughout, or however you want to structure it.
Awesome. Hi everyone. I'm Adithya. Thanks so much for having me. And today I'm a PhD student at CMU. And today I'm going to be talking about our research on augmenting language models with text compression tools. And specifically, the research question that we are trying to answer is, can we use a hybrid method that combines long context language models with text compression systems for multi-document summarization or in general for long input tasks? And feel free to interrupt me anytime to ask clarification questions or anything you would want for me to answer during the talk. And I think we should also have plenty of time at the end to have additional discussion. So before I dive into the core part of my talk and the overview, I want to just give a brief understanding of what multi-document understanding is. So let's say we have collections of documents and we have a query or we have a question that we want to answer based on the document collection. And usually this is a very expensive process, and in many different fields, a lot of people do this on a day-to-day basis. For example, journalists comb through a large collections of news articles to create timelines of events to understand what's happening every day. And market analyst looks at quarterly reports from companies and also any additional information to understand how different stocks are performing on a day-to-day basis. And as researchers, we also do a lot of multi-document understanding when we are curating our related work and trying to understand what are the most important problems that we can work on in our own research. So there are many applications of building NLP tools that can help us do multi-document understanding in a more accessible and like a fast fashion. And most of my thesis research is centered around this particular problem. And in today's talk, I'm going to be focusing more specifically on a particular subproblem. And what I want to talk about is we use language models for a lot of information synthesis tasks. And I'm trying to make a case for why we want to augment language models with standard text compression methods so that we get better multi-document performance, both in terms of system performance as well as efficiency. And in this talk, I'm going to break it down into three parts. The first part of the talk, I'll present the case for why we need both long context language models as well as compression and why each of them on their own cannot solve this problem. And then I'm going to go into our work on how we augment language models with compression tools. And finally, before I conclude the talk, I'm going to highlight some open problems that I think are the most interesting research questions in this space. And I would love to have discussion at the end on all of these three parts of my talk. So a brief overview of multi-document tasks. So this is not something new. There's a significant amount of literature on multi-document question answering or multi-document summarization for over 2 decades now. There has been a lot of shared tasks, including document understanding, conference, TAC, and TREC, where people have tried to build benchmarks and systems that help with complex question answering and summarization. And we also have released some benchmarks in this regard. And I'm going to highlight one of our works from EMNLP 2023 on background summarization. And the core idea of this work is, let's say you're following a news event. And if it's a complex news event, you see updates on the event on a daily basis. And if you're just tuning in to the news event and you don't know anything about what happened in the past, can we automatically generate a background summary that will help you better understand what's happening on any given day? And I'm going to explain this work in more detail to motivate multi-document summarization. And there are also a lot of modern applications of multi-document tasks. And specifically, we have seen lot of deep research kind of applications coming from all the top AI labs that helps you ask complex queries, and the model will first retrieve a large number of documents before synthesizing a final response. And I think we are just getting started on what we can do with in this area. And for for a long period, we didn't have our language models or our NLP tools were not good enough to tackle some of these challenging tasks. So first, I want to give a very quick overview of our background summarization work, just to motivate what a complex multi-doc summarization task looks like. This is work with Kevin and Marcus from my internships at Amazon, and this is from EMNLP 2023. So let's consider this example. What you're seeing here is basically a news update from the judicial trial that happened after Michael Jackson passed away. So you're seeing a news update from November 29th, 2011. And the update says that Dr. Murray is sentenced for 4 years in jail, and judge found them to be guilty of continuous pattern of life and deceit. So let's say you didn't follow this news before and you are just tuning in. And if you look at this update, there is a lot of information here, but you don't have enough context information on who Dr. Murray is, how are they related to Michael Jackson, and why were they found guilty. So if I want answers to all of these questions, and if I'm a news reader and I have not tuned into the event before, the best way we can do this is we can unravel the whole event, starting from June 25th, 2009, when Michael Jackson passed away, all the way to the current day, which is November 29th, 2011, and see all the news updates that have been published during this period. And we can go back and identify the most important parts of previous news updates and compile a background summary, which you're seeing at the top, that essentially gives the news reader all the core information that they need to make a better, for them to better understand what's happening on the current day. And we can generate these background summaries at any point in this timeline using all the prior updates. And this is a super challenging task, even generating from the news updates. And even in when we published this in 2022, not a lot of systems were pretty good at this task. But given that summarization has seen significant progress in the last few years, handling complex multi-document summarization tasks is increasingly feasible. And what else can we do on this task? So our dataset only looked at all the previous news updates, but an extension of this dataset could include all news articles that are published on the topic in prior to the current day. We could also take into account what user preferences are and what their general interests are. And we can also include information such as how much does the user already know about this event. For example, if I have followed the Michael Jackson's trail for maybe a year, then I don't need to read everything that has happened in the past. All I need to know is what happened in the most recent time. But if I'm only starting to follow the event, I need much more information in my background. So this is also a thing that we can factor into the background summary. And additionally, we also want to have some sort of world knowledge about all the relevant entities and events that are covered in that event. So there's a lot of information that could go into generating a background summary. And I look at this task as a good example of what a complex multi-document summarization looks like. So given that we have kind of established what the task we are solving, the first part of the talk, I want to talk about how do we approach solving these kind of problems. The traditional way, before we had language models that supported 100,000 context window, was to do some sort of text compression, reduce the size of the input, and feed it to the model. But now we have language models that support 100,000, 1 million, or even 10 million context window. So is one of these the best solution for this task? And we basically do an analysis of this and show that we want to have a hybrid approach. So to solve this task, what do we essentially need? One is we want long-range attention mechanisms, such as, let's say, sparse attention, where we interleave local and global attention. And another way we could do this is we can scale position embeddings by, let's say, adjusting rope theta. So we want the transformer to be able to do long range reasoning. An alternative is we can do some sort of input compression. And I define compression as essentially a view of our input. And we can create this view in many different ways. So one is we can do retrieval to identify the most important parts of the parts of our input. Or we could do some sort of pre-summarization where we summarize the input into smaller pieces of text or embeddings. So these are two kind of complementary approaches, but most of the work in the literature were only focusing on one of these, and we didn't find a good paper that kind of contrasts these two approaches on multi-document summarization. So that's what we do. First paper that I'm going to discuss is how do these two methods compare against each other when we try to do multi-doc summarization. So this is a work from NAACL 2025. And in this paper, we essentially analyze how compression methods stack against the full context approaches for multi-document event summarization. This is joint work with my advisor, Teruko Mitamura. So to briefly contextualize the task, our goal is, let's say, to summarize 100 documents. And these 100 documents correspond to about 100,000 tokens. And if one option is we feed everything into a language model and directly generate a summary. This is what I refer to as a full text or a full context summarization. An alternative approach is we first identify what is the most relevant part of the input, depending on the query, and then we only summarize those documents. So in the second approach, we are pre-selecting what is important before we generate the summary. So it's often much more scalable because you can work with any number of input tokens. And the goal of this analysis is to see which of these systems are better and if one of them fully solves the long context problem. In terms of systems, we explore three models from three different classes. We look at Llama 3.1, both 8 billion and 70 billion. We look at Command R model from Cohere, specifically the 32 billion model. And we also look at a hybrid Mamba and transformer model, Jamba, which is a 52 billion mixture of experts model and 12B parameters active at any point. And the reason why we picked these models was all of them support at least 128K context window, and all of them have competitive performance on a long context retrieval benchmark, which is ruler in our setting. For compression methods, we look at retrieval augmented generation. Specifically, we use Salesforce embedding 2 to embed both the query and the documents. And we pick up to 32K tokens in our retrieval setup. The reason why we pick 32 is all of our systems that I presented in the previous slide, so pretty good performance up till 32K. After that point, we traditionally see a drop in performance. We also explore some iterative summarization methods, specifically taking inspiration from this work. And one approach is hierarchical, where we first summarize documents individually before creating summaries of those summaries. The other approach is incremental, where we summarize documents in order and while maintaining like a running summary of the input. So the iterative summarization approaches don't really require a long context window because at any point we are only looking at max one document, but they are a multi-stage process. So typically they could lead to error propagation, but we wanted to see if that is actually a concern for multi-doc summarization. In terms of datasets, we use summary of a haystack. This is work from Salesforce, which is a synthetic dataset generated from GPT 3.5 and GPT 4. We also use background summarization, which is the work I presented earlier. And we also use WCEP, which is a news summarization dataset with articles taken from news websites and summaries coming from Wikipedia. All of these datasets are significantly multi-document. So for each example, you have typically somewhere between 75 to 200 documents per input. And the summaries are relatively short. So this is not a long form text generation task, but the inputs can be really long. To understand how these systems perform.
Sorry, just a clarification question.
Yeah.
Is the behavior of those data sets that you're evaluating against, are they needle in a haystack like in that they are to do well on them, you're supposed to find the relevant facts from within those multi-documents and compose them to form the answer, or are they synthesis like for you?
They are a mix of both. So summary of a haystack is actually inspired from needle in a haystack, but it is more like a multi-needle in a haystack. So you need to retrieve up to, let's say, 30 documents from a collection of 100, and then you do synthesis over those 30 documents to give the final response. So they are not like simple retrieval. You do need synthesis after retrieval, but the amount of synthesis that you need varies considerably between datasets. You need a lot of synthesis for summary of a haystack and background, but for WCEP, if you can find the right document, typically your answer is located within 1 or 2 documents. So it's a much simpler task compared to the other 2 datasets.
Gotcha. Thanks.
And for performance, so for the summarization task, all of the results that I'm going to report in this talk are using auto ACU metric. This is a model-based metric that measures how similar the reference summary is to the system summary. And it has much higher correlations with human compared to Rouge. So we mostly rely on auto ACU. And these are the results when we do a comparison between all of our methods. So what you're seeing in this plot is in any given cell, we have different data sets in each row. We have different summarization models in each column. And the baseline in each cell shows the performance of the full context setting, where you feed all the input to the model, and we limit the input to 128K tokens. And relative to the full context, we report the performance of hierarchical method, incremental method, and retrieval. And I want to highlight like 3 observations here. The first observation is, even though all of these language models claim a context window of at least 128K, their performance at that context window is significantly different. And the reason why we also pick these models is the long context strategy is quite different across Llama, Command-R, and Jamba. So we also notice that effect on their full context performance. The second observation is retrieval can often be helpful, especially if the query is like super well defined. For example, for summary of a haystack, the query is really well defined, and we do see the impact of that on retrieval, and it does show improvements in performance. But for WCEP, which is like the query is not available, so we just use a generic query, we don't see any benefits from retrieval. But the third observation, I think, which is kind of surprising to us, was hierarchical and incremental across the board show poor performance compared to the full context baseline. And this was interesting because the prior work on book summarization did find hierarchical and incremental to be beneficial. But across all of our settings, we found that hierarchical and incremental like worsen the performance over full context. And when we analyzed, we did some qualitative analysis. What we found was hierarchical was essentially generating super abstract summaries, especially at higher levels. And it was ignoring information such as like values and numbers from the summary, which is super important if you're trying to do query focused summarization. And the incremental summarization method is suffering from error propagation because we have multiple stages in the summarization process. The deeper you get into the summarization process, the noise in the input is affecting the system performance. So both the iterative methods, hierarchical and incremental, were underperforming, but retrieval can be useful.
Aditya, I guess like based on that, it sounds like this is an artifact. Like how much of this is an artifact of like the choice of end task? Because then that it sounds like the takeaway then is the way that we use these models. Like there's probably exists like end task, multi-doc summary end tasks that are very abstract generation like, in which case, you would just get a completely different like conclusion from this, right? You would actually want that type of behavior. Is that what you're saying here?
Yes.
Okay.
So definitely depends on the actual end task. So that's why we see like different performance across like summary of hashtag, background, and WCAP. For example, you don't see that much degradation in performance in WCAP with hierarchical and incremental because the answer is super widespread. So you can get the answer from different points of the input, and even if you have a lot of noise in the input, it doesn't affect because the answer is widespread. But in something like a summary of a hashtag where you need to pick multiple needles and then synthesize, uh, losing information through abstraction could be a problem. So it totally depends on the end task. And I think that's exactly why when we use these on book summarization, an abstract summary is pretty good for summarizing a book, but it might not be a good choice for query focused summarization.
Thanks. The other question was, you mentioned something earlier about like the choice of these models. They have very different long contexts. I think I missed it. Like just like I'm trying to contextualize how similar or different these models are with respect to their long context interventions, such that you would still see these findings as constant across them.
Yeah, good point. So for example, for Command R and Llama, and though for example, like the Llama model, both of them adjust theta, but Command R only just does theta existing and like adjusts the theta, increase the theta value and does nothing more. But Llama also has additional long context like training on top of it with multiple stages. I think that leads to a slightly better long context performance compared to Command R. But another thing we noticed that is very strange and which is not unique to our analysis, it was also found in ruler benchmark, was that if you look at the performance of Llama 3.18b and Llama 3.170b, Llama 3.18b does slightly better on summary of hashtag than Llama 70b. And similarly on ruler, they found that at 128K, 8b does perform better than 70b. And I think a reason for that could be that the Llama 3.1 model, the 70B model, is not well trained for long context. That's why you're getting like subpar performance. So that could also be one of the factors in like why we see performance difference.
Cool, thanks.
So yeah. So the main takeaways, like I mentioned, retrieval can be useful. Hierarchical and incremental at least underperform in the multi-document setting. But one question that we kind of found through this analysis is, can we improve the retrieval augmented setup even further? And one of the points that I mentioned earlier was that we fixed the retrieval length to 32K tokens, mainly because 32K was a reasonable enough number in terms of the ruler benchmark. But fixing this number could lead to subpar performance because we saw that different language models have different capabilities in dealing with the long context window. So maybe some language models could work with 64K tokens, whereas some of them could only work with 16K tokens. So fixing it every setting to 32K was kind of suboptimal. So in the next work, we kind of dig deeper into this to see if we can optimally find what is the right amount of tokens to retrieve before we feed it to the long context language model. And before I dive into our work, I want to highlight one prior work from Google that does this comparison between long context language models and RAG. And we use this as a motivation for our own work. So what you're seeing here is a plot from this paper from ICLEA 2025. And this is a plot for RAG accuracy on long context question answering. On x-axis, they have the number of retrieved passages for the question answering task. And on y-axis, they have the accuracy from using a particular number of retrieved passages. And what you're seeing here are results using E5 retriever. So it's a dense retriever. And each plot within this shows the performance with different question answering system. And if you look at the trends in this plot, for all the smaller models, which are 7B, 9B, and 12B, you see initially an increase in performance and then suddenly a quick drop in performance. The initial increase is expected because as you retrieve more passages, your recall goes higher. So you have a higher likelihood that your gold answer is retrieved correctly. But if you retrieve too many documents, then you're essentially adding noise to your model. And that could lead to like the drop in performance on the final question answering task. And if you look at the trend in Mistral model, even though it supports a very long context window, the peak performance that you can get from a Mistral setup is actually if you retrieve somewhere between 10 to 20 documents rather than 100 documents. And another notable thing you can see here is as your model size gets bigger and bigger, and the biggest model they evaluate is Gemini 1.5 Pro. Gemini 1.5 Pro doesn't show this drop at all, even if you retrieve more than 1,000 passages. And the reason for this, I think, is twofold. One is Gemini 1.5 Pro is much better at long context than any of these smaller models. So it's able to deal better with the noise in the input. And even if you're really retrieving like a lot of irrelevant information, as long as you have the gold answer in the input, the model is really good at finding it. So you mostly see like a flattening in performance. But a key difference here is if you use a slightly different retriever, if you replace the dense E5 retriever with a sparse BM25 retriever, the whole plot looks entirely different. So the peak performance you observe across all of these models is at a very different number of retrieved passages. So you need to retrieve more passages if you are using a weaker retriever because you want to improve your recall. And the peak performance is very different across these systems. But the trends are still very similar. For weaker models, you see an increase in performance and then a drop. But for stronger models like Gemini, you see it plateauing after a point. So when we saw this, and when we wanted to improve the RAG setup, one key question we asked is, how do we find this context length that is giving the peak performance? And if our goal is to get the best possible RAG system for any given data set, and if I'm limited to using a 9 billion model, how do I find the right amount to retrieve? And can I do it without using goal labels? These two plots were plotted using the goal labels, but I can't do this on my downstream dataset without looking at every possible context window. So this is our motivation. How do we get the best RAG performance? And how do we do this without using the goal labels? And that's the motivation for our work. And this is a work with my advisor, Teruko Mitamura. And this just got accepted at Colin. So the key research question is typically when we do RAG, in any single RAG step, we decide how many number of tokens to retrieve. And given our experimental configuration, which is a combination of dataset, retriever, and summarizer, can we estimate this number of tokens to retrieve without having to look at the goal label? And the reason why we want to do this is we want to retrieve enough tokens that we have sufficient recall, but we don't want to retrieve too many because it adds to the input noise. But we also want to take into consideration how good the long context abilities of our summarization model are. If the summarization model has very limited context window, then even if we want to retrieve more, we just can't feed it into the model. But if it's a model like, let's say, Gemini, then the long context abilities are really good. So we have more flexibility on how much to retrieve. So there are a lot of factors that go into deciding what's the right number of tokens to retrieve. And the goal of this paper is essentially to find that. But before I dive into all of it, I want to show what our baselines are. So we picked 3 baselines. First is, of course, the full context baseline, where we don't do any retrieval. We feed everything to the language model, which is our summarization system. And it depends on how much the language model can take. If, let's say, it can take 128K tokens, we feed all of the data. But let's say if it's limited to 32K, we do RAG at 32K and then use that as the full context baseline. But we also use estimates from existing benchmarks. And we specifically focus on 2 benchmarks, Ruler and Helmet. These are widely popular long context benchmarks, and pretty much every long context model that comes out tries to report their scores on these 2 benchmarks. And both of these benchmarks essentially give you an effective context window for any given language model. And we use this effective context window as the maximum amount that we want to retrieve in our setup. A quick recap of Ruler and Helmet for anyone who's not familiar. So ruler is a synthetic retrieval benchmark, and they evaluate LM's performance at different context windows, starting from 4K all the way to 128K. And they identify the effective context window relative to the performance of how Llama to 7 billion does at 4K. They read that as the baseline. And if you look at this table from the ruler paper, for Llama 3.170 billion, their effective context window is 64K, even though that it claims it to be 128K. But for Llama 3.18 billion, the effective context window is only 32K. So we use these numbers as an estimate on how much to retrieve. We also look at Helmet, which is an improved version of Ruler, and it looks at a variety of tasks, not just synthetic retrieval tasks. And we focus on two subtasks within Helmet, specifically long question answering and summarization, and use the estimates on these two subtasks as our baseline estimates. So of all these baselines, what is actually missing in these long context benchmarks? Why can't we just rely on them to identify what's the best possible length for any language model? So I think these are really strong baselines. They are evaluated on a collection of tasks. So you can easily look at these benchmarks and identify, okay, for Llama 70 billion, I'm going to use 64K. I'm not going to exhaust the full context window. But the problem here is they are completely agnostic to what kind of retriever that we are using. And going back to the plot that I showed earlier, retrievers can have different effects on the system performance, and they do not take that into consideration. The second thing is they do not take into consideration about how your downstream data set looks like. They do include a variety of data sets within them, but let's say you're trying to evaluate it on a new domain or a data set that's custom to your application. Its behavior could be very different from what it has been evaluated as part of these benchmarks. So in this work, we try to also include these two factors and see if we can do better than what Ruler and Helmet can achieve. And we essentially address this gap. So now I'm going to give an overview of our method and then dive into individual components. So typically the pipeline looks something like this. You're given a data set. You want to retrieve the most important documents. You pass it to your summarizer to extract the summary. The baseline estimate is you look at an existing long context benchmark, identify the effective context window, and use that as your retrieval estimate. But what we do instead is we first subsample a small set of the data set. So let's say we have 100 examples in the data set. We sample 25 examples, and each example has a collection of documents as input and the system generate like a reference summary. We leave out the reference summary. We don't look at the goal label, but instead we pass this sample subset through a panel of language models. In our panel, we include Llama, Jamba, and Quen, and we create a set of silver reference summaries. So these are approximations to what the gold summary looks like. And we use this silver reference to create that plot from Jin et al., where we have number of retrieved tokens on x-axis, and then we have the F1 score on the silver dataset on y-axis. And we essentially run the RAG pipeline on this subset and see where we can find the optimal performance. And once we identify this optimal context length, we can take that length and run our full RAG on the entire dataset and evaluate the model. The core idea of this method is we don't need to run our estimation on the full dataset. We can just work with a small subset to understand the properties of the dataset. And we don't need to use the goal label. We are approximating the goal label with a set of silver references. And this method actually works really well. We beat ruler and helmet-based estimates across a variety of models. But before I dive into the results, I want to highlight core parts of our method. So sampling the subset of the dataset is one part. Using the LLM panel to compile silver references is the second step. Once we find the silver references, we search for the optimal context length by running RAG across a range of context windows. And then finally, we use that optimal length to run RAG on the full dataset. For silver panel, we try to pick the largest models that we could run on our setup. Specifically, we picked models from different classes. We used Quen 2.5 72B, Llama 3.370B, and Jamba 1.5 Mini. For long context LMs, we also select two very long context language models, specifically the Quen 1 million context window model and Prolong 512K, which is an extension of Llama 3.8 billion. And for generating silver references, we sample 25% of the data. We collect 3 summaries for each LLM from our panel. And then we use MBR decoding to pick the top silver references. So we sample more than necessary, and then we identify the top 3 most important ones. And the reason why we do MBR decoding is we can't just rely on one single model references. We want to identify, like remove any outliers and pick the most frequent summary. So we sample multiple from each model. So we create 15 candidates. And then based on prior work, we use the same utility metric as our downstream evaluation metric, which is A3CUF1. And then from this re-ranking, we pick the top 3 as the silver references. And once we have the silver references, we search a space of context windows all the way from 8K to 80K in multiples of 8K. And then we pick the smallest length that gives a score within the standard deviation of the max. And the reason why we pick the smallest is we want the system to be as efficient as possible. And we just finally run the full RAG on the full data set. For results, we evaluate them on the summary of a haystack dataset. The dataset has up to 128K tokens in the input. So it's not like super long context, but it is at the limit of most of the models that we evaluate. In terms of retrievers, we use 2 retrievers, GT 1.5B and GT 7B. These are Quen 2 based models. And we use A3CUF1 score to determine the summary quality. In the first set of results, I have the summarization model for each row. We have 3 baselines, the full context baseline, the ruler baseline, and helmet baseline. Within helmet, we have estimates from the summarization task and the long QA task. In the final column, we have the performance from our estimate. And we look at models at different sizes. So we want to see how our method works at like 0.5 billion models all the way to 72 billion. And also wanted to see how it does across different model classes. And what we find is generally our system, like all the retrieval methods do better than the full context. The full context is not comparable. But our method also improves upon the baseline methods in most settings. We see similar results for GT7B, and the empty blocks that you see here. So we only report ruler and helmet whenever there's an estimate available from the prior benchmark. And we again with 7B retriever, we see that our method performs at least as good as the baselines, or most of the times better than the baseline. But we also wanted to understand 2 specific points here. Specifically, will our method work for really long context models? And will it also generalize to models that are not part of our silver panel? So first part is, what do they do when we have a really long context models? So specifically, we look at the Quen 2.5 models, which have 1 million token context window. And we also look at Prolong model, which has a 512K context window. And on the baselines, these methods have very strong performance. So all ruler and helmet estimate their effective context window to be really high. But we actually find that the effective context window on the multi-log summarization is much lower. And on our dataset, on the SumHay dataset, we found the performance of our method to be significantly better. So our method also works on very long context models. And to make sure that we are not just evaluating on the silver, like the Llama, Jamba, or Quen model, we also evaluate on 5.3, which is not part of our silver panel. And in this case, we see comparable performance to ruler. Helmet does slightly worse than ruler and our method, but our method is at least the best or close to the best in all of these settings. The key takeaways we have from this work is If you can explore your dataset, your retriever, and summarizer, and estimate and get the estimate retrieval length for your experimental configuration, it often tends to be much shorter than what any of these long context benchmarks report. So at the end, your method would be more performant, but it also can be more efficient. And another thing, another reason why I think compression could be useful is for larger models, running them on a very long context windows can increase your inference latency. So identifying a context window that's much shorter with the same performance can be a lot more efficient. For smaller models, which does not support long context windows or their long context performance is really bad, identifying this length estimate could lead to a much more performant setup. Some next steps that we're exploring is we want to try more compression methods, and we also want to expand the silver panel and tasks. And finally, I want to dive into some open problems that I see in the space and some interesting future directions that people are working on right now and potential solutions for them. So the first open problem I think here is most of the analysis that I talked about today is focusing on inputs that are length of like hundreds of thousands of tokens. What if, let's say, we want to solve a much complex task that involves hundreds of millions of tokens? And one example I can think of here is, let's say you have a query focused summarization task where your input consists of all the documents in the web, potentially past conversations you had with the model, and additional user metadata. One example I can think of would be background summarization, and where you want to be able to generate a background specific to each user and by looking at all the data from the web. How do we go about solving this task? It's almost clear that we can't just use a single language model context window to do this, because even if the context window is 10 million, that cannot fit all the data that we have on the web. So we need something that could work with much longer inputs. So compression, I think, is absolutely necessary. And there is no single form of compression that could solve this problem. And I think some of the more recent works that we have seen, for example, multi-agent cloud research, uses a different form of compression. So one sort of compression is you want to compress all the prior user conversations into memory and keep track of them. And you can also have a search tool that is compressing information from the web into the LLM's context window. So the way multi-agent systems work, you have a lead agent and you have a bunch of sub-agents just doing the search task for you. And this is not just a long context problem. This requires a lot of additional skills. You need reasoning, you need retrieval, you need memory and long context. And the goal of each of these sub-agents in a setup like this is to compress information to feed it back into the lead agent. But I think one of the questions that we as a community have not answered sufficiently well is, how do you determine what the structure of your compressed output looks like? For example, what model are we going to use to create the memory? What model are we going to use for search? And what would be the length of each of these compressions that we do as a part of this multi-agent system? And what is the format of each of these compressions? And I think we are barely scratching the surface here. And depending on how much compression you do, your model can be a lot more token efficient. And currently, from Anthropic's report, their multi-agent system uses 15 times more tokens than a single LLM. And this can be infeasible for a lot of applications. The second direction, which I think is super interesting, is can we make small language models better at doing complex reasoning tasks? And the main goals here are we want to improve long context performance, and we also want to improve reasoning abilities. There have been recent works in this direction, and two works that I think are super interesting are Qwen3 and SmallLM3. How do we make sure that small models are good at both of these tasks? And I see two potential solutions here. One is we want to figure out the training recipe that will help improve both long context and reasoning. And the way SmallLM3 does this is kind of super interesting. They have a mid-training phase where they increase the context window of the model, and the post-training phase that adds the reasoning abilities. But what they found is after reasoning step, they found the long context performance to drop. So their solution was to do model merging between the long context checkpoint and the reasoning checkpoint. But I think this feels a little bit of like not, it's not very clear this is the best way we can achieve both of these skills. So there's a lot of work we could do in this domain. Another solution I think is instead of trying to improve the context window of small models to a very large value, we could limit them to, let's say, 32K or 128K, and instead focus on combining a collection of small language models so that we have a much larger effective context window, because we can use context windows across multiple models. But each of these models, we can train them specifically for reasoning tasks. So overall, instead of just relying one small LM to solve the complex task, we can use a collection of models. The third direction I think I'm very interested in is evals. Specifically, how do we curate evals for complex synthesis tasks? And we can't have one evaluation setting for different parts of the model development. We need something that is easy to run, potentially like a QA style benchmark during model development, because we want something fast that's easy to verify. And I think BrowseComp from OpenAI is a very good example here, which is easy to run, a complex task, and easy to verify. The final evaluation, I think, should always be human evaluation, but it's not clear what's the best way we can approach human evaluation for these tasks. And I think there are two directions that community has already identified, but I also want to highlight like how we can improve those evaluations. The first evaluation direction that I see is like expert return checklist. There's some work from like Samaya AI that does criteria eval, where experts will write checklists on what they expect the reference, like the system generated summary should contain. And then given like a system generated summary, you match it against the checklist. And depending on what percentage of the checklist is satisfied, you give a score to the model. These I think are very valuable. They are super suitable for fact-based tasks, but they are not very scalable because you need significant investment in to the domain experts to curate these evaluations. We have done some prior work in this direction where we did model-generated QA checklists for backgrounds in our EMNLP work, but I think there's a lot of potential here. The second direction, which is a very recent work from Semantic Scholar, is Science Arena, where they compare summaries generated from different models and ask experts to rank them. I think these are a lot more suitable for open-ended tasks where writing a checklist could be very difficult. But an issue that I see with this line of evaluation is it does not force the expert who is evaluating to read the input documents. So the problem here is when comparing two summaries, we are essentially evaluating if one of the summaries is missing things that the other summary mentioned, and then judging whether that missing aspect is important or not. But what we are not checking is there could be things that both the summaries miss, but it's present in the input. And the expert doesn't really know that because neither of the summaries have mentioned it. I think one thing we could make this better is, can we make it easier for experts to read a long input? Currently, if you are like, there has been some work from UMass on this specifically for book summarization. But if you want the experts to rate summaries from, let's say, any collection of 100,000 tokens, the only way I think we can make this happen is instead of showing full inputs to the user or the expert, we can show compressed versions of the input to the user. And the user can selectively then go ahead and explore like full documents underlying the input. And for scientific literature, this kind of looks something like we show the summaries of the outputs. And then for each of the cited papers, we first show the abstract. And if the expert thinks that this particular paper is important, they can read the abstract and then go into the paper and explore individual section summaries and then the full paper. So we don't show the full document to the user. We let them like selectively expand the search space. Another I think evaluation style, which I feel is a gold standard, is evaluating the systems in the wild. There's work called Copilot Arena, which is for code LLM evaluation, where They show like when you look at text like code generations in Copilot, instead of showing just one generation, they show generations completions from two different models. And depending on what the user picks for code completion, it automatically gives a preference rating between two outputs. I think this is like the ideal way of evaluation because you are actually evaluating it where the user is utilizing the system. It's not as clear what this looks for, like that's an information synthesis task. But having an evaluation system like this, I think, would be a good direction. In summary, uh, the goal of my research has been on how do we build hybrid long context and text compression systems for complex information synthesis tasks. And I talked about three specific works from my thesis: background summarization, long context versus text compression, and hybrid methods. And some open problems, I think, are how do we scale to much longer input? How do we make small language models better at these tasks? And finally, how do we develop evals for these? And yeah, thanks for taking time. I'm happy to take any questions.
Cool. Thank you. We have time for a few minutes for questions. I can start with one and then people can kind of hop in. I think it's sort of like a more general question, Aditya. A lot of what you're presenting is, to me, it looks like it's if you have a model that can do some reasonable amount of long context, here's the best system you can set up so that you can like maximally use its inference for solving these problems. But I'm kind of curious, like from the perspective of, well, what if I actually want to build the good long context model in the first place? Do you think that there's any of these ideas around text compression that you're proposing, or interaction between text compression and RAG, can be used to help supervise like the development of the long context model in the first, like directly?
Interesting. So is the goal to increase like the context window of the language model itself?
Either that or let's say if either that or inducing a particular like nicer properties of like long context model able to handle these types of operations, synthesis or summarization operations intrinsically.
Oh, that's a really good question. I think so. At least right now, for long context reasoning, at least most of the benchmarks that I see are focusing on retrieval. Like, so you have a query and you're trying to retrieve from a very long context. Sometimes you have multiple needles, and let's say the MRCR benchmark from like OpenAI or from Google, you have multiple needles, and your goal is to retrieve these and then do synthesis on top of it. But I think what we are currently missing is we are not exhaustively forcing the models to do synthesis over every part of the input. So let's say you have 100 documents in the input, and we don't have tasks or data sets and like even like documents that will force the model to utilize every single document from the input. I think I do see a significant potential for using synthesis, like synthetic tasks that force the model to pay attention to every part of the input, and we could use that to do long context like pre-training. In terms of compression, I think so. One direction that I've explored, but not with a lot of success, is compressing part of the input into embeddings and leaving part of the input as raw tokens. And the reasoning for this was compressing into text could be very lossy because we are essentially summarizing the input and we don't have enough, like we may lose important information. But compressing into like dense vectors, I think would be a lot more promising approach. But based on my experiments, I didn't like there is some work on prompt compression, but I didn't have much success with like creating like compression into embeddings and then augmenting that into the model input. But I'm not sure if that maybe there are other ways to explore it, but I haven't had much success in that.
Cool. Thanks. Does anyone else have a question? All right. If not, then let's thank the speaker one more time. Yeah, cool. Thanks, everyone. Thanks, Adithya.
Thanks, everyone.
Thanks, Adithya. And then I'll be in touch when I have an update to share with you.
Awesome. Thank you.
Thank you. Bye.
Bye-bye.
Bye.